Okay, let's continue. General Chemistry Part 15. At the end of Part 14, we did not have enough time to finish these sections, and there's a little left. So we continue, we will finish pretty soon. Now we will talk about electronegativity for different elements in nature. They have a different ability to attract the bonding electron during bonding formation for a compound. Now, Linus Pauling devised this scale we call electronegativity for us to use it to judge if the compound, mostly binary, is going to be a polar molecule or non-polar molecule. We normally call polar molecule as ionic, and non-polar or covalent, and or in between we call polar covalent. The compound has nature of polar nature as covalent nature as well as ionic compound nature. Now there's, as I stated in the last section, we talk about ionic or covalent, just like we talk about the purity of matter of any kind, species in universe. There is no such thing called pure substances. So there is no clear cut 100% ionic or 100% covalent. There's something always involved a little bit in purity. Some ionic compound may have a certain percentage of covalent feature, or the covalent compound may also contain some percentage slightly ionic. So that is not very clear cut. That's the nature. So we have to respect that. Before we get into a clear-cut detail, we have to think about this just like that's everything happens. There's no such thing called 100% of anything, right? So using this electronegativity on the periodic table, the periodicity of electronegativity for elements, and we know, and on the left-hand side, most metal, they have the value of electronegativities right under 2. Something close to 1, most of them, and on the left. And if you approach it to the right up corner, which is close to the non-metal region, the elements inside that region normally have the electronegativity is larger than 2. 2.5, 2.3, 3.5, 4.0 for fluorine. Some of the periodic table author give 4.1. All right, but the lowest is 0.7 down under the lower corner, left corner of the periodic table, right? And so when we talk about make a judgment of the chemical compound, either as a polar ionic, or non-polar covalent, or in between we call polar covalent, and we use that table to try to find the difference of the electronegativities from the two elements involved in the bonding formation. If the difference for the electronegativity is under 1, slightly under 9.9 something, and then that is going to be very, very covalent. Or the difference for chi, the delta chi, is larger than 2.0, basically larger than 2.1, then that is most of the compound, the binary compound, will be very ionic. Between 0.9 to 2.1, that range we call polar covalent. So that is what we started last session, part 14. We did not get finished. And then we involved this, the last presentation of this table for the ionic character as the y-axis from 0 to 100%. All right, and then the curve goes up and it's getting close to ionic nature, goes down close to the covalent nature, but in the very middle, the horizontal axis, like x-axis, consider the electronegativity difference between the two elements. Then we have scale only 1, 2, 3, 0, 1, 2, 3. No need to be bigger because we can find out no difference between any elements will be larger than 3.1. 3.4. It's 4.1 minus 0.7. The biggest difference on the periodic table for fluorine and the francium is going to be 3.4, right? 3.4. So there's no need for more than 3.5. But from here we are able to figure out if the difference between two elements make a binary compound, right, is covalent or ionic or polar covalent. We just have to find out their electronegativity on this chart and then find the difference, then fit into this diagram, this graph, then we find out it's going to be ionic or covalent or in between, right? So this diagram brought to my attention when we have this crisis, a virus crisis, we're supposed to use the school announced Canvas to do the online teaching, and some other instructor offered me her own developed the course, and I gladly accepted the offer, and I distributed this homework and assignment and reading assignment to my class for this class to read. But then I went there, I found some alarming mistake. Now that is one of them I mentioned in a couple email correspondences with you in this class, and then I'm going to talk about this particular one here today. On the canvas, the first reading assignment, if you go to the quiz or something, that's fine. We already talked about that, has a lot of mistake in there. The canvas, the first reading assignments, talking about aluminum carbide. Now, aluminum carbide has a chemical formula is Al4C3. Considered alumina has a +3 oxidation state, and carbon has -4 oxidation state. Now this is what I'm going to teach this way. I do not call them charged because they are not charged. Simply they are not. Why? Because this compound is not ionic compound, as the book posted down there for you to read, for you to study, for you to learn. The whole thing is totally wrong, because let's go by the classical diagram right here, right? The ionic nature versus the delta chi, the difference of electronegativity right here. See my red laser light, right here. Now, between the aluminum value here, aluminum value is 1.5 right here, right? And the carbon is the diagonal corner, and just like above the aluminum is 2.5 right here, right? As I mentioned in the past, or I mentioned a couple times, these two, the carbon was largely by most of the author considered as non-metal, but I say no, it is not. We mentioned that it has luster if it's graphite, or the diamond has luster, right? Diamond is very, very beautiful, it's shining, right? That's a metal feature. And the carbon make charcoal, that's very dirty, powdery. It's non-metal feature. So this one, carbon right here, supposed to be by definition considered as a semi-metal, right? Aluminum, the same thing. We already mentioned once, the last part, 14 or 13. We talked about aluminum combined with 3 oxygen, 3 hydrogen, can either consider as aluminum acid or aluminum hydroxide, which one is, right, H3Al O3, aluminum acid, or the Al parenthesis OH subsequent 3, that's aluminum hydroxide. The alumina can be fit into the generalized format for acid and the base, right? Of course, acid will be oxyacid with oxygen. Very well. So, if the acid involves what? Involve non-metal elements in the middle. If the base, right, OH, involve metal elements on the left. So these elements actually very well be a semi-metal, not a metal, right? In chemistry, per se. But most of the scientists, most of the chemists, most of the teachers teaching chemistry, they use this as a metal. Of course, aluminum look like a metal. Most of its feature is metal, right? You can make a utensil, make all this aluminum. Even this camera on the tripod is aluminum. I'm taking the video, right? Making the video right here. Aluminum is metal, but also has a lot of non-metal feature. But anyway, these two both concentrated the position in the periodic table right over here next to each other. So the electronegativity value between these two elements are so close. Look, carbon is 2.5, right? Well, barrier, I guess. And aluminum is 1.5. So the difference, delta chi right here. Carbon and chi and aluminum is 2.5 minus 1.5 is 1.0. Now check this diagram. If the 1.0 right here, the difference right here along this line, it's the borderline of covalent and the polar covalent. It does not say that is the borderline between covalent and ionic, because there's a huge difference, almost 1/3 of the space on this line, on this graph, belongs to this polar covalent. It is not ionic, not even related, so far away. The difference is either you call it polar covalent or you call covalent. So this is a covalent compound. Alright, aluminum carbide is a covalent compound. It is not an ionic compound. So that is a mistake, a huge mistake. And the book written by more than 100 authors did not realize something is not right. And then give you as a beginner, the entry-level learner chemistry, and you are a sheet of blank paper, and you are not supposed to get all these mistakes. It's just like a contaminated white paper, and then no longer it's white enough to draw a beautiful picture because it's already been tinted, right? Your mind is corrupted, right? So I try to set records straight right here to tell you the book got a lot of mistake. Only one assignment and one reading assignment already involve more than 2 or 3 mistakes. That is very alarming. That is not a good textbook use. At least not for the beginners. For me, I am able to distinguish right or wrong, but you don't. So we need to change the textbook. That's not a good one. But I don't have the authority to do that, right? So I do my part to point out what is right, what is wrong, okay? So this is my point. So I only make this much, and I don't want actually make too fussy over this. Let me see, my clock is not ticking, that's fine. Alright, we got 15 minutes. Now, so if we understand this, then the last part we're going to talk about the train of electronegativity, or the periodicity of train of electronegativity for elements on the periodic table. So let's using this area. All right. Oh my God. As we see, the value of electronegativity for elements in the periodic table goes, probably already mentions briefly, goes from the left to the right along the period, getting bigger, increase the value, and also going from the bottom of each family up is value getting bigger and bigger. So the first alkaline metal and 0.7 all the way to 2.1, which is hydrogen on top of lithium, right? The same token to the halogen, right? To the halogen, and go 2.5, even lower, that's less than that, 2.8, 3.0, and 4.1 fluorine, right? Even we sometimes move the hydrogen on top of fluorine, that's only the case when the hydrogen combine with a metal to form compound, and then that is considered as a collagen family member. So that is the one possess a oxidation state as -1, right? That's time hydrogen. So we have a homework, if you remember, and the homework or the small test we did, and I asked you to actually the answer. There's only 2 elements in each choices, and which choice those 2 elements involved, they have exactly same numerical value with absolute value of their numerical oxidation state, but has both plus and minus. Now here we go. Hydrogen, if you put here is -1, if you put here is +1, so hydrogen can be plus minus 1. Another one is carbon right here. We already talked about it. Carbon right here. Remember that. We give you the periodicity or periodic trend for oxidation state, right? The carbon can have -4 and the +4 both. So plus -4 as the oxidation states for carbon as elements in the chemical bonding formation, and show the oxidation states, right? So these 2 are the answer. Which one you remember that? Now, let's do 1 or 2 examples, right? Using the diagram right on the left of ionic percentage versus the electronegativity difference to determine the type of, or not type, polarity. The polarity of compound. Now, let's say first one between carbon and let's see, carbon and oxygen, right? Carbon and oxygen. Now we have carbon and oxygen. If the carbon and oxygen form compound, let's say carbon monoxide, right? So carbon monoxide. Let's say carbon monoxide. So what is the nature of the compound? Ionic or covalent? Let's see the chi, right? The chi for carbon minus, or let's say oxygen is bigger, right? Oxygen bigger, and the chi for carbon. So what is that? Oxygen is 3.5, right? 3.5 minus carbon is 2.5. Then the difference exactly 1.0. So what do you say? Of course, it's covalent, right? It's covalent, right? Is that right? So we pick another one for, let's say, potassium, right? Potassium and what? And let's say potassium and oxygen, right? Oxygen, they make a compound, right? What compound will it be? What kind of formula do you think? Potassium is alkali metal, always +1 only, right? And oxygen, in most cases, -2. So what is chemical formula? Chemical formula must be K2O, right? Right, K2O. So what is a compound? So we find out, so the difference for for the electronegativities, and oxygen is bigger, and then what is the potassium? It is 0.8, right? So 3.5 minus 0.8, what is that? 2.7. Of course, 2.7 will drop into this region, right? 2.7 right here. So the percentage of ionic is very big, you know, it's not 100%. That's nothing 100%. So that's ionic, right? Ionic. So if I give you this kind of a problem, of course you should be able to answer. That's a piece of cake, am I right? So you should be able to do that. And then let's see, if you have a boron nitride, right? Boron nitride is between boron and the nitrogen, right? Now the general form, right? There's a several, 3 or 4 different kind of a structure for boron nitride, right? Some are very soft, some very hard, and the melting point is 2,800 degrees or something, even higher. And it is a good, insulator, and it can be conductor as well. So it is a strange compound and very new. It's not very new, but decades ago they don't even have that. So boron nitride, what is that? So that is the general formula, Bn, right? Let's say, so the chi for nitrogen minus chi for boron. So what is nitrogen? Right? That's the carbon, then next to nitrogen. Nitrogen is 3.0. 3.0, boron 2.0. So the difference is 1.0, not 1.0, where is 1.0? That's going to be right here, right? So that is where boron nitride. So it's very close to what? To almost 100% of a covalent. This side of 100% ionic, boom, down here, close to 0 must be what? 100% covalent, right? So that's okay. So if that's the case, then that's covalent, right? We consider covalent. Now, aluminum chloride, we already talked about it. It's 1.0 is covalent. It's not. So what is polar covalent? So polar covalent, right, is right here. We talked about hydrogen fluoride, right? And the hydrogen and the fluorine, right? So the hydrogen fluoride, it's a gas molecule, and the chi value for fluorine minus chi value for hydrogen. This for fluorine, let's use, we already did that, I just erased it, right? Let's use 4.0, right, instead of 4.1. 4.0 minus what? That's a fluorine, that's instead of 4.14. And then that is, I'm probably afraid of, so, and what is the hydrogen? 2.1, right? 2.1, so you have 1.9, so 1.9 was that right under 2. So this is dropping to this region right here, 1.9, right? 1.9 right here. So that is what? Polar covalent. All right? Is that good enough? Yes, we think so. So we got a couple minutes left. So now the last thing we talk about Chang, the very last. I don't remember the number here. I don't know, maybe 4, whatever 4. There's a trend, the periodic trend. Trend of electro it's what? It's we are talking about. From left to right, each period is getting bigger, and from bottom up, each family is getting bigger. So we talk about the getting bigger on both sides, just like you consider this is a slingshot. We already mentioned that, right? And then there's a rubber band, and you put a rock in the middle, and pull up the rubber band and stretch it, and then release it. The rock is going to go this way and that way. No, they are not. The rock is not going to go this way, nor that way, but it's going in the middle, right? That's just a diagonal shooting up that direction, go out. So we have a combined effect for electronegativity is going from the left lower corner of the periodic table increase to the upper right corner of the periodic table. Basically start from francium all the way to fluorine. You said don't there's helium and neon. No, they are not our concern, because why? They barely form any compound. They are inner gas, noble gas, right? Not until krypton and xenon or argon have a very limited number of compounds, because they are not very chemically reactive, right? So we do not need to worry about their electronegativity during bonding formation, attracting electrons over or not. we consider as, just forget about it, and consider as not related, and then the value of electronegativity is going up to the, so you're going this way, or going this, so they all, you have the trend is diagonally, from a lower left, right, corner, all the way increase to the upper right corner of the periodic table. That's enough? Yes. Alright, so we finished that part, and then we are able to use this in the future. Now I am about time to erase this. Then what is this? So we finished the electronegativity chi bonding polarity part 4. Now we are getting to reactions. Now we really were getting to reaction because while we talk about compound, we talk so many different things about a chemical compound, their nature, their, you know, and then we haven't reached every aspect, but we're getting there. For the next section, we talk about chemical reactions, right? So let's erase this whole thing. We're getting to erase. Now we already talked about one part in my lecture in the past. We talked about chemical reactions. We have to involve 5 or 6 basic concept, most important concept, right? So we're gonna get into there and then get it started. In the next section, part 16, we'll get into full scale, full swing on chemical reactions, starting from the classification of chemical reactions, their driving force. What is driving force means? What driving force means? What is the back reason, right, to make this reaction become reality, make this reaction happen, right? So who is pushing that reaction? What is the, we call driving force? What is the force behind this whole reaction, driving the reaction going one direction or both direction, and then what is the cause? So who's pushing that reaction to happen? That's what we're going to talk about. Then we talk about how to balance chemical reactions. Alright, we're going to talk about the tips of balanced chemical reaction. Nowadays, a lot of teachers don't even know how to balance chemical reactions. They didn't learn. Their teacher, their own teacher, did not teach them. So they thought it was not important. But it is important. You all have my handout, right? I emailed to you, right? The title is The Art of Balancing Chemical Reaction Equations, right? And it starts from the scenario and what's going on nationwide about chemical reaction. Nobody cares. Nobody cares about chemical reaction balancing. Nobody cares about quantitative analysis of chemical reaction. Now we talk about